Dr. Nilanjan Dey, sir. Am I audible? Dr. Dey, sir. Please unmute, sir. Dr. Dey, sir. Am I audible? Sir, please unmute.
Yes, Ram, I'm here. Dr. Ram, I'm here.
Yeah, thank you, sir.
Hello.
Hello. Yes, sir.
Yes. Yes, yes. I'm here. I'm here, Dr. Ram.
Yes, sir. Sneha, ma'am.
Morning, all of you. I hope I am audible enough.
Now I request our colleague Sneha, ma'am, to introduce our speaker, Dr. Nilanjan Dey, sir. Sneha, ma'am, please.
Thank you, sir. Our Honorable Speaker Nilanjan Dey, sir. Thank you, sir, for having a session for us. And please allow me to have a brief introduction about you. May I? Okay. Nilanjan Dey, sir, is an associate professor in Department of Computer Science and Engineering at the GIS University, Kolkata, India. He is a visiting fellow of University of Reading, UK. He also holds a position of adjunct professor at Ton Duc Thanh University, Ho Chi Minh City, Vietnam. Previously, he held an honorary position of visiting scientist at Global Biomedical Technologies, California, USA, from 2012 to 15. He was awarded his PhD from Jadavpur University in 2015. He is the editor-in-chief of the International Journal of Ambient Computing and Intelligence, which we commonly known as IGI Global. He is the series of co-editor of Springer tracks in Nature-Inspired Computing, that is also known as Springer Nature. Series co-editor of Advances in Ubiquitous Sensing Application for Healthcare elsewhere. He has written over 85 books and 300 publications in the area of medical imaging, machine learning, computer-aided diagnosis, data mining, and many more. He is the Indian ambassador of the International Federation of Information Processing, Young AICTE Group, and senior member of IEEE. Thank you so much, sir, for sparing time for our session. We are so grateful to have you as a speaker in our ATAL FDP program.
Thank you, Sneha ma'am. So a very good morning to all of you, Dr. Ram, Sneha ma'am and all, and a very happy Teachers' Day. So am I audible?
Yes, sir. Happy Teachers'
Yes, sir,
Day.
you are audible.
Okay, fine. So as this session is a very introductory session, so I'm going to talk about deep learning in medical imaging and the challenges and the state-of-art solutions. So
Sir, your voice is not clear.
so machine learning application. Hello, is it fine now?
Yes, sir.
Hello, is it fine now? Hello, just a minute, please. Let me just give me 2 minutes.
Sure.
Hello. Hello. Am I audible now?
Yes, sir. Yes, sir. You are audible.
Okay, fine. So actually there is some internet issue. Okay, 1 minute. So any machine learning application is very much depends on very much sensitive to the data which you are using for the training purpose. So if the training data is not of high quality, then lots of issues will be faced in machine learning. Again, I'm repeating. So any machine learning application is very much depends on or very much sensitive to the data which you're using for the training purpose. Now, so ultimately, we get garbage out. Always data we have made up observation. We not understand your target. Now, always we want big clean data. And if you train your system with bad data, so-called bad data.
So, excuse me, sir. Sorry to interrupt you in the middle.
Again,
Actually, your voice is still not clear enough, and sharing is not done properly.
okay.
Yes, sir.
This is frustrating. 1 minute, please. Just a minute. Am I audible now? Hello.
Yes, sir.
Yes. Now I think actually there is some issue in my internet. So screen is all visible, correct? Hello. Hello. Yes. The screen is visible?
Yes. Sharing, sir.
Any machine learning application is very much depends on much sensitive to the data you are using for the training purpose. So it's typically you can say that machine learning algorithm where the data is a fuel. So that fuel data, if it is a bad data, ultimately affects the modeling. So we need to ensure that what data we are using, it should be a very high quality data. Now that's why this is called the garbage in, garbage out. In machine learning, if you give garbage, ultimately you will see end of the day you are getting garbage out. So we have to always train our system looking at a target, what type of target we are expecting. So for that, good data and bad data, that needs to be identified. Now, the very first process is called the data cleaning process, because most of data which are not clean data, and we have to identify the non-erroneous data. And for that cleaning purpose, if you not clean the data, end of the day, it will negatively impact the all prediction model. Now,
Sorry
that
to interrupt.
you have to find out the
Sir, audio is clearly audible, but still is not visible, sir. I think you should share once again. Audio is clear, sir.
okay. It is not visible till now. Hello. Okay, now is it fine?
Yes, sir.
Audible and
Yes,
visible
sir.
both. Correct?
Yes, sir.
Yes, sir.
Okay, okay. So let me start from the very beginning. Okay. Okay. So what I'm talking about, that any machine learning application is very much depends on or very much sensitive to the data which we are using for the training purpose. So whenever you are giving garbage to the learning system, actually end of the day, we will get garbage as an output. So the training data, when we are using, we have to always look into the target. And always the data which we receive or which we use for the training purpose is not a clean data or not a so-called good data. So there is a method or mechanism which is called the finding of the clearing of the data. So the data cleaning process is to identify or correct the error data. If you not correct the error data, ultimately it will negatively impact the predictive model. Now, what is bad data? Bad data means inconsistent data, extraneous text. Maybe suppose if you have an MRI or a CT image and there is some text. So that is called the extraneous text. There can be missing data. there can be redundant information, contextual error, there can be garbage value. So all these are typically bad data. So whenever we are getting some data, it's not always a good thing to use that for the training purpose. We need to pass through a proper cleaning process. If you not clean that data, maybe bad data will negatively impact the predictive model. So that's why finding out the bad data is the first and foremost thing once you use any machine learning algorithm. Because all good data sets are alike, they are almost similar, but bad data sets are bad in its own way. Because all different bad data sets, you have to dig individually and you have to find out what is the error in that particular data. So in this way, we can clear the data, we can use the data for the training purpose. And this is the hungriness or the data hungriness of machine learning. So we know that data is the fuel. We know that any machine learning algorithm, they are very much hungry. I mean, they are hungry about the data. But it's not that blindly we will use any data for the training. We have to use so-called quote unquote good data. Now, is there any standard rule, means how much data we need for training? This is one question. So do we have our own heuristic method which will actually decide that how much data is required for the training? There is no as such so-called mechanism. Like suppose if you are working on, say, survey data, say you are collecting, say, survey, or there is a survey of questionnaire. So there are lots of questionnaire and you are collecting from a sample pool. Maybe there may be 377 is a value, which is a good number if you come up with a rational decision from a questionnaire based survey. There is a website you can explore, which is called RowSoft. In RowSoft software, you can see there is one, I mean, if you give the different value, the error, the reliability score, etc., ultimately it will show you that if you take 377 number of sample from a data set of 20,000, you will see that you can come up with a rational decision. I'm talking about the survey-based study, like questionnaire. Once you are taking the question, passing the question and taking the inputs, and you are collecting the data. But for machine learning, how much data is a good number? So getting data or clean data is very difficult. The answer is as big as it should be. We can use that. So always we will look for the sufficient amount of data. If we get data, more data, the generalization will be better. Now, let's think from other point of view. Deep learning is nothing but a memorization. It's typically a memorization technique where we use the training set and we try to come up with a model of interpolation. Now, what is the missing part? The absence part is the underlying variables relationship. And we can't come up with a proper decision until we try to understand the underlying relationship amongst the variables. Now, what is the major limitation of neural networks? The major limitation of neural network is its very limited capacity to deal with the variations. It actually not able to deal with the variations. To make them understand the variable data, we need lots of possible all aspects of variations of data, which we use for the training purpose. So again, I am repeating. In deep learning framework, you will see that the most missing part is the absence of relationship building in between the underlying variables. So we don't know what is the relationship in between the variables. And ultimately, it affects the decision-making process. So any neural network, they don't have the capability or the capacity to deal with the variations, variable data. So to overcome this, what we need lots of data and lots of variable data. So all type of variations we require, which will actually cover all possible aspects of variation. So in deep learning framework, this out of data distribution or say normal or non-adversarial data, which are very common in our real life setting, those type of data, the variable data, the variant data, It's need to be injected to the system to overcome the limitation of the capability of a neural network not to deal with the variable data. So that's why we need data. Now coming to the other part, if you see deep learning, we are actually long way from integrating the abstract knowledge. We don't know what the object are, or what the object for, or how they are typically used. We are not that much bothered about that. We get good result and we are happy with that result. But we always not try to find out the abstract knowledge or the inherent pattern in between this. So we are actually long way from integrating the abstract knowledge. Now, if you look into a 7-month-old infant, you will see he can also understand, or sometimes he can also extract the knowledge or the rules, but the deep learning fails. Even he can do from a very small number of unlabeled examples within few minutes. But deep learning, the lack of mechanism of learning abstraction, it's failed to find out the abstraction, the variable definition. So that's why we need more and more data. As much as good data, if you use for the training purpose, the system, the mechanism will be more generic, more robust. So that's why for robust deep learning algorithm, how robust it is, that need to be tested. That is one thing. And second thing is, what will happen if we don't have adequate data, adequate or quality training data, or enough quality data? So these are the two biggest questions: how robust the deep learning algorithms are. And the second question is, how much data is good data for the training purpose? So we will try to find out these two questions answer in our next part of the presentation. So first thing is why we need data. And once you get the data, how robust the system can you form? These are the two typical questions. Now, think from the very beginning. Suppose there is a single point and we are trying to fit a polynomial curve. Now, if we increase the number of points, you will see the polyfitting will be much more better. And if you more increase the points, you will see you will get a more generalized version. So as the number of data increases, the generalization will be much more better. Am I audible? Hello?
Yes, sir.
Someone is writing, I'm not audible. Okay, fine. So second thing is, suppose there are very few number of points, and if you come up with a linear regression, and if you try to incorporate more number of points, you will see the linear regression will be much more, and the point estimation will be improved. So more number of data points, that means more number of generalization, more better generalization. So starting from the polyfitting, and if you go to the linear regression, and if you think about, say, KNN, if the KNN number of data points, if you increase, the prediction class will be much more better. And if you think about, say, any kind of hierarchical structure, you will see the hierarchical structure, the tree splitting due to the data will be much more better. So in this way, we can come up with a decision that the number of points need to be incorporated, more number of data points. So more number of data points means the generalization will be much more better. So for more better generalization, we need different data points. So again, first thing, for better generalization, we need more data points. Okay, now the problem is, what's wrong with small data? If we don't have adequate data, what is the problem? So those two problems I will try to discuss. What is the problem of small data set? If you don't have adequate data, what will be the problem? The very first problem is, if you consider a very small amount of data, mainly it will revolve under a very high variance. And the first thing is overfitting. Because if the number of data is less, always the chances of overfitting will be high. And the second thing is outlier. Means if there is noise presence, you will see ultimately the noise will be dangerous if the data size is less. So because suppose if you are considering say 5 data and 2 are outliers, and if you are considering 5,000 data, 2 are outliers, then definitely the first one, once the data is less, outlier is higher, that will be more dangerous. So that's why there are 2 typical reasons. First is it's always roaming around or revolve around a high variance, and the 2 typical problem is less amount of data always there is a high chance of overfitting, and the second one, the presence of outlier, it will be sometimes dangerous one. So that's why dealing with small data always a typical problem. Now let's think from say a little bit history. Professor Lee from Stanford University in 2009, they come up with a huge database. What is the size of the database? The size of the database is 14 million. And how many numbers of classes are there? 80,000 distinct classes are there. 80,000 distinct classes. Now they try to categorize, they try to classify. So from 14 million data set of 80,000 distinct category, they try to classify. How many numbers of intermediate layers you require? How many numbers of parameters you require? Try to think about this. So initially in 2010, the error rate was 28%. Then from shallow machine learning, once we dip into the deep machine learning in 2012, suddenly the error rate decreased 10%. That is from 26 to 16%. And gradually, after 2015, the error rate is getting lesser than the human error rate. So you can imagine 14 million data set, 80,000 distinct class, and it is lesser than the human error rate we already achieved by deep learning. But how many numbers of parameters you require? Professor Hilton in 2012 from their group, they reported that if you consider a 9-layer convolution neural network, only 9-layer convolution neural network, how many numbers of parameters? 60 million parameters and 6.5 lakhs nodes. 60 million parameters and 6.5 lakhs of nodes you roughly required for 1 million data set distinct categorization of 1,000 categories. Just to categorize 1,000, you need 60 million parameters and 6.5 nodes. And I am talking about 80,000 distinct categories, not 1,000. So you can imagine how many numbers of parameters you actually required for this, and how many numbers of node you required for this. So this is huge. That means the number of parameters which you need to be tuned and the number of intermediate nodes, that is a huge number for this. But still, we are now achieve the accuracy. So it's a very high accuracy, and the error rate is lesser than the human error rate. We're actually going to 100% accuracy in that. I mean, maybe in the next future coming a few years. So that's why in this way, you can imagine that the large set of data, once you deal with, we need to deal with large number of parameters, large number of intermediate nodes. And that is the biggest challenge in deep learning, to deal with those parameters, to deal with those nodes. So what we can say, the success of any deep learning framework actually depends upon typically few things. One is how many numbers of parameters you are using, the millions of parameters which you are using. You need first hardware to train. And the last one is you need lots and lots of data. So the performance of any kind of vision task actually is logarithmically increase the volume of the training data set. So model size, the data size, and the complexity of the problem domain, it's always directly proportional. Yes, it is always okay to invest time and money to gather more and more data. Because if you get more data, more clean data that will be actually affect the overall system. So that's why we have to deal with the parameters, we have to deal with the hardware, we have to deal with the large scale leveled data for a successful deep learning frame. Now, let's come to the medical image processing, or say healthcare data. The biggest challenge of healthcare data is the limitation of annotated data, because we always need to benchmark the result. So if you are coming with a segmentation result, that result need to be benchmarked, which is already benchmarked by some medical expert. And then you compare these two results, and then you report that how good your segmentation is, maybe based on the F measures or etc. So generally, this human wants try to annotate, or the doctors wants to annotate. It is always a time consuming task. And mostly you will not get the medical expert who don't have adequate time to annotate all those. So we always get a very small data set, because hand annotation is time consuming. Second thing is, once you deal with medical data, we are dealing with, there is always a privacy laws are there. So which is called the patient privacy law. And patient privacy law is different for all different countries. And there is a data security issues are also there. Data privacy laws are there. So because of these all limitations and the patient consent, so the collection of data is always limited. So in medical imaging, we will always face one challenge, the annotated data. Because getting annotated data from the doctors, time consuming, there is privacy concern issues, and there is also patient concerning issues. So always we happy with 500, say 1000 patient data. If you're able to get 500 data or say 1000 data, we are happy with that. So think about it. One deep learning framework we are deploying for 14 million data. And other side, same or similar type of framework we are using for 1000 data. So think about the imbalance. And from there, actually, we try to come up with a rational decision, generic, decision. One side, we are dealing with that number of data, 14 million. And other side, we are happy with 500 or say 1000 data. So data is important. Getting data in medical imaging is sometimes, or most of the time, is a very hard task. So that's why the first challenge of deep learning framework, once you deal with, that is dealing with small data or limited annotated data. There are a few databases which are very standard database, starting from say abnormal data, say abdominal data, or say brain data, or the breast data, cardiac data. If you think about all these data sets, if you look into this data, you will see the data size is not that much. Like say NIHCT data, it only contains say 82 number of samples, or say lungs data, or say prostate data, PROMIS. These size are very less, but we have to work and we have to deploy our deep learning framework in these public data sets. So sometimes it is becoming a very, huge task for any kind of imaging guy, because they are working with a very lesser number of data. So first challenge, or the biggest challenge, is the annotated data, there is a crunch of annotated data, very less number of data set. So first we have to deal with this once you work with deep learning framework. Okay, so until now, am I audible? Can you please give a feedback? Dr. Ram, until now it was fine. Okay, fine. Thank you. Okay, so once you have very less data, what is the solution? Because as I said, in public data set, if you think about it, most of the cases the data set size is very, very less. So we have to augment the data. And there are some primitive technique, means as an old technique of data augmentation, which is called image manipulation technique. So you can increase the size of the data by a couple of times, say might be 3 folds or 4 folds. How can you increase it? By some basic image manipulation technique. One type of manipulation technique is called the geometric transformation. If you have a original image, you translate it, you rotate it, you flip the image. These are called the rigid augmentation technique. Apart from these, there are some other techniques called stretching or say sharing. Say you are randomly zooming a part or say zooming out a part. You are taking left or right button in this way. So you are giving a move to the left or move to the right in this way. So these are called the linear augmentation. So if you have a single image, original image, from that image based on the geometric transformation, you can create multiple images. So if you have a CT images of 100, from that 100 CT data, you can come up with 1000 data by geometric transformation, by translating, by rotating, by a certain degree. You can change the degree also. You can flip it, you can zoom it, you can stretch it, etc. So these are very old techniques. Apart from these, there are a few other techniques like, say, you can change the contrast level. You can change the deformation, elastic deformation. Sometimes it can be too much deformed. You can color augmentation, you can do, like you change the histogram equalization, white balancing, sharpening, etc. So in this way, you can create your data set, which is actually augmented data. So from one base data, you create multiple data. There are other few techniques, latest techniques like random erasing. Part of the image you erase and you continue the process and you can create multiple images from one particular image. Or you can go for mixing the image. There is a foreground or background and there is an alpha tuner. And by that alpha tuner, you are taking something foreground, taking something background. This is called the blending technique. So you can overlay or blend. In that way, you can also mix the image. You can number of data set you can increase. Or you can go for say kernel filtering. Like suppose if you have a single image, from that image you change the variance of the kernel in different variance level, it is giving different images. So in this way you can create multiple objects from a single image. So these are all primitive techniques. It's not very new. Image multiple, I mean, this manipulation technique and coming multifold images are not very new technique. But think about it. What is the main problem of these all image manipulation technique? Any image are actually generated from the base image. So somehow all the generated image are biased because whatever you are doing, you are stretching or you are shifting or you are rotating, you are erasing, you are blending, you are changing the kernel filter. Multiple images are generated, but all those generated images are actually generating from a parent image. And somehow all these are biased. So that's why if you are dealing with a CT image and you are rotating it into multiple degree, you create multiple images, but all those degree rotated images are actually base image is a common image. So even if you create multifold image, but all images are depends upon the base image. So it is a biased one. And once you give a biased data to a classifier, you will see the result is not good. It's not like if you have a single X-ray, you cut the X-ray, you cut it into 4 pieces and you have 4 data. It's not a good idea because we can't partition data, same data and put considering different data and put it into classifier. It should be always biased result. So it's in this way. If you go for multifold data, if you go for augmenting the data, end of the day, you will be frustrated and you will see the classifier is not performing well because whatever the data, multifold data we are using, somehow all data are biased data. So that's why people think about the GAN. What is GAN? This kind of adversarial network where we actually try to transfer one image to another image. So suppose if you have a winter scenario, you change it into an autumn scenario, or a summer scenario, you change it into winter scenario. So in this way, we can change the image we can translate. And this particular GAN is very much robust and computationally that is intensive. So as it is very costly process, we need always a cheaper solution. So what is a cheaper solution? One cheaper solution is called the neural tile transfer. So we will talk about these two things. One is called the GAN and another is the neural tile transfer. So neural tile transfer is nothing but it actually grabs the texture or the ambience or the appearance of an image and it try to mix with the content of other. What is the content? Suppose these particular images, these city images are all real image. Again, it's not audible. Someone is writing.
It's okay, sir. It's okay.
Hello.
It is clearly audible, sir, and screen is also visible.
Okay. Fine. Okay. So these particular images are true contrast image, true city images. And these particular images are synthetic images, which is GAN generated images. You can, I mean, if you look into very closely, you will see these are contrast stretch, these are non-contrast stretch images, but these all images are synthetic images. But this is not generated by manipulation technique. These are all generated by GAN. So we'll talk about a little bit about GAN, what is GAN and how it actually works. And another thing is neural tile transfer. Like suppose if you have a texture, if you have an ambience, that appearance you can fade into another image and you can create another image. So in this way, changing the texture, changing the appearance, you can also change the number of images. So here I am trying, say, study night, that texture, I try to put into different images and I try to form different multifold images. So these two things we will cover. We will try to talk about the augmentation using GAN and another one, augmentation by using neural tile transfer. Here is one example of neural tile transfer. This is the style. The style is the great web of Kanagwan. And here this style we are putting into this MRI. And after 4 iterations, you can see this particular is a neural tile transfer image. And these all are different 4 neural tile transfer images. So from one base image, by transfer the style, we can create multifold images. In this way, one image can be 5 images and all are different. They are augmented data and you can use this for the training purpose. So this is the example of neural tile transfer. So let's talk about GAN. So GAN, there are 2 different modules. One is called the generator and one is called the discriminator. So what is generator? Generator always makes fake images and this pass to the discriminator. So suppose if you have a latent space, this space is basically the noise Z, which is generated maybe the uniform distribution or by the normal distribution. So this Z pass through the generator. Generator creates a fake image, suppose a fake rose or a fake MRI or a fake CT images, and that pass to the discriminator. Discriminator have a real set of MRI or CT images, and it try to discriminate that is that image sent from the generator is a fake image or it's a real image. Now discriminator task is always it try to classify. It try to classify that the image sent from the generator is a fake image or it's a real image. Now after that, if it is in this way, there is a tussle goes on and that always generator try to create more realistic data, more realistic synthetic data. And sometime it might happen the discriminator failed to find out that the same data by the generator is a fake data. It's not a real data. In this way, we can create exactly similar kind of data like rows. Now think about it. Once the noise Z is passed through the generator, it's create an image X. That X is passed to the discriminator. Now what happened? Like generator, it takes the noise. There is a theta 1 tuner. Generator creates an image which is called X. Now X passed to the discriminator, and there is theta 2. Discriminator with a probability of 1, 0, it tried to classify that the data sent by the generator is a real data or is a fake data, or is it in between. So in this way, this theta 1 and theta 2 is basically the tuner. So there is two parts. One part, we try to form an image from the noise space. Second part, the noise which is sent from the generator, we try to classify based on the probability that is it real data or is it a fake data. Now, as a result of the discriminator, what happens? We try to do two things. One is we try to maximize. Second thing is we try to minimize. What we try to maximize? We try to maximize the probability that the real data X is always belong to the real data set. And what we try to minimize? We try to minimize that the probability of the fake data, it never goes to the real data set. That means the true data, the correct data, real data, and second part is minimization. The fake data should not go to the real data set. So it's a maximum where we try to maximize one part and we maximize the other part. Real go to real, fake doesn't go to the real. And after that, if you think from one other point of view, the discriminator is basically a classifier. So once there is a classifier, there is always a chance of loss or error function. So classifier will do mistake, or there will be a loss, or there will be some error. And always we try to minimize that error. That is our objective. Now, how to minimize it? There is a log function. If you consider log loss, do any kind of error, if the penalty is very high, then the chances of doing mistake will be high. What I'm saying is, if the error is less, then the penalty will be high. That means the chances of doing error will automatically getting lesser. That's why we use log loss. And after a certain point of time, after several points of time training, you will see there is an objective function where one side we try to maximize that the real go to real and the fake go to the, it should not go to the real data set. That is our objective. And we always try to minimize the loss function. After several steps of iteration, one point it will come where generator will not be able to create more realistic data. And the discriminator will discriminate that this data which is sent by the generator is a fake data. So it's a win-win game. And whatever the data we are getting from the CAN system, it's almost looks similar, which is called a synthetic data, which is called a multifold data generator. So in this way, we can create multiple data. It's basically based on the Nash equation of game theory, min-max game, where we try to come up with trying to oppose the loss function, optimize the loss function. In this way, this is one way we can create multiple data. We can increase the data. GAN is one solution which actually helps the deep learning data crunch. The second, until now it was audible. Is it audible? Hello. Am I audible till now? Okay, fine. Thank you. Okay, so the second way is to increase the number of data or solving such type of issue is called the transfer learning. So transfer learning, like if you have different tasks to solve, and if you have different learning system, so you solve different challenges with different learning system. Now I am giving you a problem, and you are using the preset or the frozen knowledge for solving that. Let me clear it. Suppose if you have a huge data pool, huge data set, public data set, and you can extract the feature, you can put classifier training, etc. Now I am trying to solve a problem where the data set is very less, maybe 50 or 100 or say 200 data. And this data is say 2 lakhs. So from 20 data or 200 data might be I'm not be able to solve or come up with a rational decision. So what I will do? My objective will be I will try to impart the knowledge which we gain from this learning system as a frozen knowledge to this for solving the challenge of this particular thing. So this frozen knowledge, which is called the pre-trained knowledge, for solving a task B is basically called transfer learning. So transfer learning is a way of solving when the training data is very less in size. We try to solve that problem by a pre-trained model or a frozen layer, which actually solved another problem where the data size was huge. So the number of parameters rather than GAN, here it is lesser and computationally not that much of expensive. That's why transfer learning is very widely used in, you can see, in medical imaging. Because most of the cases we have crunch of data. Once you have crunch of data, we try to solve it, the problem domain, by solving other problem in other domain, and we try to pass the frozen knowledge for solving a medical imaging problem. So it looks like something like this. There are two different types of data set. These are similar type of data. These are all histological data. Or this one are typically different types of data. Etc. So they are once you do transfer learning, the first module, the initial phases are actually trying to capture a low level feature. And the feature, they type low. Once you use any model, the initial layers actually try to find out the low level feature. And last one, they always try to find out the subject specific features. Now here, what we try to replace? Hello. Okay, so the second is once you try to load the pre-trained model, then we try to replace the final layer. To replace the final layer, we try to replace the final layer with specific feature of best transfer. So these particular layers are actually replaced by specific cancel classes. Then if you train, if you go for training the network, if you deploy, ultimately you will get data probability, which is much more better. So in transfer learning, we sometimes can tune our result. That tuning can be done in this way. So where we replace the final layer with specific feature. Yes, please. Hello. Am I audible?
Yes, sir. Yes, sir. It's okay, sir.
So this is the second one. The third way, another challenge is called one-shot learning. Now, what is one-shot learning? One-shot learning actually refers to a problem where you teach the model is one instance, a single instance. So the learn to re-identify the instances. I'm giving only one time data and you have to identify. In fact, there is a zero-shot learning. So model cannot look any example for the target during the training. So during the training, it will not look into the train rate. The one-shot learning, your model observe one sample only. But it can be K short learning. Only K number of observation it will look. So only K number of example it can go through. For face recognition, this one is widely used by Siemens. So in this is NVIDIA. These generated faces, all those faces are fake faces. So these faces, if you try to find it out, the major challenge of one shot is hello. 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 Is it fine now? Hello. Okay. Fine. But this Cisco is taking too much bandwidth. Okay. See, if there are two images, two figures which contain same dog or same cat, then it is very difficult. So if you are using any say GAN generated image, it's very difficult for one shot. So person identification, say wearing a hat or a scarf or say glasses, so any scarf or something like this, it's very difficult to identify the person. So these few challenges are there in one-shot learning. And in medical image, there is a benchmark work in 2015. You can go through this particular paper, how one-shot learning unfold in the brain. There are very few work has been carried out in this area. It's a huge area to work. One-shot learning or say zero-shot learning or K-shot learning. How can you use this for medical imaging also? But typically, we use this for face recognition purpose. But it can be used, and it is already reported in 2015. But very, very few work has been carried out in this area. So this is another way, another interesting thing. Now I will talk about patch-based training. So in deep learning, patch-wise training is very important. What is patch-wise training? We always intend to avoid the redundant part of an image which we use for the training. Suppose if you have a region of interest, there is a lesion, there is a tumor. So why should I use the for training purpose the redundant part, or say the part which is of no use? So semantic segmentation, any kind of semantic segmentation, basically we always try to classify based on the pixel. So we use always the whole image, and we actually use or rather add the redundancy as an input. So always once you consider whole image, that means you are adding redundant part or unnecessary part, or which is called non-region of interest, because you are trying to classify based on the pixel. Now that's why patch-wise training is important, because once you go for patch-wise training, during the training purpose, we always try to batch a random patch. That means a small part of the image we are looking for, that part we are using for the, or the interest part, the region of interest part we use for the training instead of the full image. So think about it. If you have n number of images which you are using for the deep learning purpose, and if you can use only the region of interest part, then it will be actually increase the overall accuracy, overall performance rather, number of parameters will be automatically reduced, which is your main objective. So that's why we should not go for pixel based one, rather we should go for patch wise training. Now for patch wise training, we have to ensure one thing, that once you are taking the input should be highly variable, because deep learning only understand high variant data. So input has enough variance, that need to be ensured. Second thing is the valid representation of the training data set. You have to represent the training data which is a valid data. So that is two important things. Then only the entire technique will converge faster and need to be balanced the classes. But one challenge is there in patch-based training, that is overlapping of patches. So overlapping of patches actually always gives you high accuracy, but it is computationally intensive. What is the meaning of that? You will see the performance will increase, but overlapping of the patches or the size of the mini patches, this actually gives you a wrong result. So overlapping of patches, somehow you have to overcome, even if you get higher accuracy. So in this way, the patch-based learning is very important. Without using the whole image, a part of the image or patch-based sampling you require. You don't require the semantic image, pixel-based one. So this is the first another thing. So here, this is the result. Say this is the input image. This is patch-based extraction you use for the training purpose, and it's called one patch in one decision, where you are trying to what you are trying to do. This is a single patch, and you are trying to single patch. You are trying to identify which type of patch it is. So you are trying to classify that. This is one patch, one decision. Or another one, if you have histological data, from there you separate out these different patches, and all those patches you can use for the training purpose. It's not the pixel-based study. Rather, it's a kind of patch-based, where you can consider the textual part, where you can consider the shape-based study, etc., etc., or maybe the color one, etc. So in this way, you can come up with a model training, and ultimately by majority voting, you can predict that this is a benign case. So these are two examples where patch-based study people actually deploy. It's not typically say kind of, you can say the image pixel-based one. Now the another one is the which is called weakly supervised learning. So weak supervision and another issue. Weak supervision means the machine learning where the noisy data is limited. What I am saying is your data set, there is a crunch of data. On the weak data, you are trying to provide the supervised signal to level the larger amount of the data. So it's an alternative of where the say, hand level data set is adequate data you don't have, which is very costly. So the alternate solution is you have to go for weak supervision. How can you do this? So suppose there is a structured data. One is high quality annotation, one is called no annotation. So if you don't have annotation, you will go for unsupervised learning. And if you have high quality annotation, we can go for large annotated data set, we can go for small annotated data set. Large annotated data set means which is very expensive, which is called the supervised learning. But small annotated data set are two types. One is called the semi-supervised learning, one is called the transfer learning. So it's less accurate, and another one is maybe a little bit of accurate. It's transfer learning kind of cases. But in between this high quality annotation and no annotation, there exists one type of annotation which is called the low quality annotation, which is basically the weakly supervised learning. So it's kind of heuristically you try identify the patterns. It's a kind of the batch annotation of cluster of data. It's a kind of using the noisy prediction from the model. So these all are typically low quality annotation. So we always deal in weakly supervised learning, the low quality annotated data. It's in between the high quality and the no quality data. It's in between the supervised, semi-supervised, transfer learning, and unsupervised learning. So this particular domain, which needs to be more explored, where we deal with weakly supervised learning in medical imaging. Though lots of work has been already carried out, but people are still working in this area, which is called the weakly supervised learning framework. So here you can see there is a whole image. It's not the patch based. There are neural network. So supervised learning, unsupervised, the transfer learning. This is one interesting part which is called weakly supervised learning, where you actually deal with the convolution neural network or the fully convolution neural network, or typically you can use for the detection, segmentation, or classification. So all these things, which actually I will cover in my later talk. But these are the parts which can be done by weakly supervised learning. Now comes the sparse annotation. Now, what is sparse annotation? So sparse annotation is kind of once you don't have annotate data, especially for the 3D cases. Once we are talking about 3D imaging, there the sparsely annotated data is a crunch of data, and we need to parse the data. How to do this? So the weight of unlabeled data are set to 0. If the data part is unlabeled, we will set as a 0. And if it is a label part, we will use that for the training. So only learn from the labeled pixel. So if you're dealing with the pixel-based study or the semantic classifier, we only deal with the labeled data, but unlabeled data should be 0. This is called sparsing, or rather sparse annotation. But the data should not be all annotated, which is very costly process. Rather, we should try to take those values for the learning purpose, for those pixels for the learning, where the pixel is labeled, those only, not the unlabeled data, which should be set as a 0. This is called sparse annotation. So if you do sparse annotation, you will see the cost ultimately of deep learning will be getting lesser. So there are lots of work can be carried out in this area also, which is called the sparse annotated data formation. Then comes the effective negative data set, which actually helps or enhance the discrimination power. So if the network on false positive cases, so you are trying to inject the false positive cases. So if you put more false positive cases, you are trying to check the system is robust or not. So you try to enhance the discrimination power. So for any kind of system, if you want to increase the discrimination power, you have to inject to the framework negative data or false positive cases. In this way, maybe for a system, maybe 40% of the collected sample are false data, negative data. So if you inject those data, ultimately we'll see the discrimination power of the entire network will enhance. So this way, we can increase the effectiveness of a learning model, where the effective negative data needs to be injected into the system to enhance the discrimination power. This is another area which also need to be taken care. Then comes the class imbalance problem. So class imbalance problem is something, a very small portion of the image, as I said, is region of interest. The remaining portion is non-region of interest. So for a particular patch belonging to a background area, you are not using or you are not bothered about that. You are more bothered about a small organ where there is some anomaly, and you have to give greater importance to that part rather than the background. So our system should not be biased toward the background. It should not got trapped to the local minimum. If you give bias to the background, your actually region of interest or the anomaly part or the small organ part, that will be somehow impacted, and that impact will got the local trapping of the minimum. So that's why what we need, we always have to give higher weightage to the foreground. The patches which are there in the higher foreground, that needs to be given always higher weight. And in the cases of this blending technique, always you should give lower weightage to the background. In this way, ultimately, it's a kind of patch-wise training where we combine the patch selection mechanism. Which particular patch need to be give much more emphasis, which particular patch we need not to give emphasis. That needs to be classified. This is basically the class imbalance problem, because non-region interest is major part. The region of interest is very less part. That's why our focus should be more on region of interest part rather than non-region of interest part, where we give higher weightage to the foreground patches. So this technique is called the patch-wise training combined with patch selection. Okay. Just a minute. Until now, I am audible. Actually, I'm really suffering from networking issue today.
Yes.
Okay, fine. Just a minute. So, what are the challenge of training deep learning models? One challenge is overfitting, as I already discussed. So, what is overfitting? So, a model learned patterns specific to a training data and which are irrelevant to other data. So, you are trying to train your system with some data which is irrelevant data, which is bad data, which is not actually that garbage. I mean, you can say actually a garbage. So we have to identify the overfitting cases. And identification of overfitting cases is not very easy task. So always we have to look into the validation matrix. We have to look into the loss and the accuracy. Now, once it sometime happen that it stop improving after a certain point of time of epochs. Means a validation matrix, you will see it stop improving. After a certain number of iteration, it stopped improving. And it started decreasing rather. So at such one point of time, it will increase sharp. Then after that, it will not increase. Then suddenly there is a decrease. And if you look into the matrix, you will see that training matrix continuously improving because you are giving more and more data. But ultimately, it's an overfit case. Sometimes it might give you 100% accuracy. So if you get say 100% accuracy, always rethink about the result. 99.9% accuracy. Rethink about the result. Look into the matrix. Are these matrix are correct matrix? Don't you think that it is an overfitted case? If you have a validation matrix, loss and accuracy, which is a very good number, we should not look into the number only. Rather, we should rethink about that the data which we are using, are we not using garbage data? Please ensure. So that's why we have to revisit that. So validation matrix is very important. We have to think about it, that accuracy, good accuracy, best accuracy is always doesn't mean the system is a robust system. The system is a very accurate system. So what we need for several manners, again, the answer is same. We need more data and good data. So lower the capacity of the model to memorize the training data. Actually, it reduces the overfitting. So to reduce the overfitting of cases, you have to lower the capacity of the model to memorize the training data. So if you able to do these things, ultimately we'll see end of the day, the model is getting more reliable. So always not go or not chase the accuracy. You look into the sensitivity, you look into the specificity, you look into PPV, NPV, etc. Then only you are able to understand that it's not a case of overfitting. So the next one, if you have overfitted data, the solution is first you have to reduce the networking capacity. So you have to remove the layers. You have to reduce the number of elements in the hidden layer, because this is the only one positive solution. If you're able to reduce the number of layers, automatically the case can be handled. Another thing is the cost of the loss function. If it is a large weight, then you apply regularization. It can be L1 or it can be L2 regularization. That is the absolute value of the parameters or the square value of the parameters. And the last solution is the dropout layers, which will randomly remove a certain number of features from a setting them to a 0. You are actually setting a certain number of features as 0. So you randomly remove. So these are the dropout layers. So somehow you have to look into the layers to deal with the overfitting cases. So in this way, you can handle the overfitting case. The another thing is the learning rate. So deep learning framework, once you are talking about learning rate, we are talking about the stochastic gradient descent or SGD algorithm. So where we try to optimize, what we try to optimize, we estimate the error gradient for the current state of the model using sample example from the training data set. So whatever the training data set, we are trying to find out the error gradient. And we try to update the weight. And the model use back propagation of the errors. And then you tune accordingly. So amount that the weight needs to be updated during the training, that actually refers to the step size of learning rate. So how much tuning you required, weight tuning you required, how much updation you require during training, that actually tells the step size of the learning rate. So the learning rate is, you can say it's a configurable hyperparameter. So if I ask you that in a deep learning platform, the framework, there is only one option to tune the hyperparameter, which particular hyperparameter you will configure? The answer should be learning rate very first. Because once you tune learning rate, which is a configurable hyperparameter, that actually affect the step size of the entire weight balancing system. So if the weight need to be updated, the training weight, it depends upon the step size, which is directly related with the learning rate, which is a configurable hyperparameter, which can be set in between 0 and 1. So in this way, we can decide that how much the step size will be. And in this way, the learning rate, actually the error estimation amount of the error for which the weights of the node in the network are responsible. So are you getting fully update that one, or you want to scale it? So that scale can be done by learning rate. We not, instead of updating the whole weight or the full amount, what we do, we use a scaled weight. That is called the learning rate. So suppose 10% of the overall weight we are using for the learning as a learning. So that means the learning rate is 0.01, that traditionally common default value. That means the network are updated 0.1 into estimated weight error. So 10% of estimated weight error at each time the weights are updated. So now the question is at this point, and very natural question, which algorithm we will go for this learning rate? There is no as such one common algorithm, but ADA delta and ADAM, these two optimizer are very widely used optimizer for medical imaging. So these two optimizer, if you use for SDG and SDG with the momentum, the ADA delta and the ADAM is the one of the solution. I mean, you can say some of the solution, but ADAM is very widely used. Yes. Now then comes the gradient vanishing. That is another problem of deep learning. Now, once you think about a back propagation neural network, so as the neural network algorithm advances to the downwards, or backwards, you can say, so gradient often getting smaller and smaller, and it approaches to the 0. So once the gradient getting smaller and smaller and approaches to the 0, eventually the input size, the input value, the weight of the input and the lower layer are nearly almost unchanged because the gradient getting vanished. So this is called the vanishing problem. So what I'm saying is, if you, the back propagation algorithm, if you look into it, if the gradient often getting lesser and it approaches to the 0, then the initial value, initial weight which you are feeding, but the lower layer is almost nearly unchanged. So that's why it's a kind of vanishing the gradient. But the opposite can also happen. That is called the exploding. What is that? It's a kind of getting larger and larger. So the gradient, the input value, in between value and the gradient, there is a huge difference. So you are trying to increase the gradient value. So gradient, say, it's an opposite of vanishing. So both these two are actually occurs in machine learning, but in deep learning, most of the cases you will face this particular challenge, which is called the vanishing problem. So vanishing gradient problem. where the gradient descent never converges to the optimum because the difference is less. As the difference of the gradient is less, gradient descent never converges to the optimum. And this is one of the challenge for deep learning because it approaches to the zero. It getting very smaller. It can't distinguish. So it vanishes the gradient. So it never converts to the optimum. So intermediate hidden layer output will be upscaled. That is the solution. So if there is no difference in between the weight, intermediate layer, the gradient is vanished, what you need to do? You have to somehow, the intermediate hidden layer output will be upscaled. And that technique is called deconvolution. It's not the convolution one, rather it's a deconvolution. You are deconvoluting so that it upscale the intermediate or the hidden layer. And then it passes to the softmax, then you will get some predicted result. There are some solutions for this, like initialization, like selection of the value or batch normalization. These are the few techniques by which you can say you can use this vanishing gradient problem solving. But this is one challenge which you have to face for deep learning, vanishing gradient problem. Okay. For typically medical imaging, there is another problem which is called the organ appearance. So if you are dealing with heterogeneous appearance, now what is that? The target organ may be of different size, shape, location. It might vary to patient. In fact, the acquisition system in which alignment the patient is, everything depends upon that. So that's why the boundary detection, where there is a limited contrast level, the target organ and the neighborhood tissue, it's very difficult to identify or separate. So the target organ and the neighboring tissue, that needs to be, the boundary needs to be identified properly, which is called the inherent imaging technique. Like for the CT images, for MRI images, everywhere, you will face such kind of problem, where the boundary actually separate the targeting image organ and the neighboring tissue. One solution is multimodality based approach, or other solution can be superpixel information. What is superpixel information? That I will discuss. So that actually helps to segment the overlapping organ part or the boundary, so that it can distinguish, this is my target organ, this is my neighboring tissue. So this is another one. Now, how the question is how robust the deep learning are. See, there is a paper which comes in 2019, which is called one pixel attack for fooding the deep neural network. So there are several images, 1, 2, 3, 4, these images. And if you omit one particular pixel, the cat will be detected as a dog. If you omit one pixel, the bird will be identified as a airplane. So this particular attack is called one pixel attack. So think about it, how challenging it is, I mean, to protect itself from getting fooled. Because one pixel can make the difference. Output will be something else. So deep learning system is quite good at some large fraction of a given domain, but it can be easily fooled. So we have to think about the robustness of the system also. So deep learning applications like in medical imaging, if you think from anatomical application, starting from the breast, liver, heart, carotid, intravascular, say your limb, your spine, muscle, what domain we can apply. Or from methodological tasks, the methodology can be detection, localization, classification, segmentation, registration. I think all these things will be covered in future sessions. Then comes the clinical task, the biometric measurement or the CAD system or the computer guided intervention or the therapy, etc. So these all three different tasks and the applications where medical image can be, I mean, assessed for the deep learning framework. I mean, you can deploy deep learning framework. And if you study, you will see the number of papers published, mostly in fetus images or in heart or the breast. majority of the work carried out in the post state, etc. And few of the area where the people are working, but in very less, like say kidney, that classification or detection kind of work has not been carried out, but segmentation, a little bit of segmentation carried out. So here, how many numbers of segmentation, detection, and classification carried out? You can see in 2017 onwards, in all three cases, the number of paper, there is a lots of paper published. So in this way, what type of deep learning framework people use? This is another way you can see that CNN majority people use. The very less one is RNN. So you can, rethink about it, which particular area, which particular modality, or which particular, say, technique of deep learning framework you will use. This is one glance of literature, means which modality and which type of imaging or which particular class of image processing technique or which particular type of deep learning framework majority of the researcher they worked on. So this will give you an insight that what type of area you will choose later. So there are a few medical competition which you can explore. You can take a screenshot of this. So these are the few competitions where it's an open competition and their data set is also available. So like skill lesion analysis, or say for tuning machine, say intelligence against the lens cancer, etc. So the Kaggle data competitions, and apart from that, there are different competitions which you can target, and the problem domains are very much defined, and data set is also given, so you can try. There are lots of medical data where that number of data, there is no crunch of as such data, like sometimes be 15,000 data or 40, say 77 different collections. So these are few of the data, just public data set you can use. There is no crunch of as such data. The last thing which I actually cover, which is basically the reliability issue. Am I audible till now? Hello?
Yes, sir.
Yes, okay. Okay, so the last thing is most of the cases, or the rather majority of the cases in medical imaging, in shallow machine learning, we put it into some medical classifier and it gives some good result, and we become happy with that, say 99% accuracy. But there is always a trust issue. There is always an issue that the practitioner will tell you that you use support vector machine, you get this result, or you use, say, a random forest, you get this result. I'm okay with that. This is good. But how much trust I can on you? How much rely on you? So that's why the performance and the explainability, these two things are very important. How much the system or the entire block learning module can explainable. So that's why if you look into this, now there is a trend that you can get any result, but you have to make people trustable that your system is robust, your system is explainable. So we have to think about deep explanation. That is modifying the deep learning techniques to learn the explainable features. What do you mean by that? Suppose there is a learning data, there is a learning process, there is a learning module, and what exactly we used to get? We used to get a predicted output. The face is a happy face. 95% accurately it can predict. 0.98 prediction. Now think about it. How did the model predict it is happy? I don't know. How did somewhere, what not some other expression, which is there in this particular expression? What did makes this model take this decision that this is happy? Which particular feature actually focusing or prominent? It tells that this is a happy face. Or how to correct the error? Why should I trust that he is smiling? So I don't know this answer. This explanation I need to provide. So explainable AI is such a kind of model which tells two things. One is the trust, and the second thing is understanding the process. So can I trust the module? I know this feature learned by the model. I know how to understand the decision model. I understand why this face is classified as happy. I know why this face is not classified as something else. I know when the model will fail. I understand how to fix the error. So I need to study the winklings around the eye. I need to study the lip stretching. I need to study the upwards or the chin bows or the muscles so that I can find it out. The face is happy. So those features which actually explain that the decision which was taken by the AI model is correct one. And this particular area, which actually nowadays required more and more work. We got good result. Our classifier gives better result. In COVID study, many of the segmentation, many of the classification cases, we reported that 99% accuracy. But what about trust? Why should I trust you? You need to give explanation. That explanation can be given by explainable AI or XAI. So this is a wide area where you need to study two things. One is explainable model. One is explaining interface. The new principle, strategy, or the technique which you are using for this. And another one is the explainable models, where what type of modeling you are coming up so that you can explain the explainability of that training model. So that the task or the user can say, psychologically explain that, okay, I understand. I understand why this accuracy is 99%. I understand why error rate is less. I understand how can I trust these things? How can I reduce the error more? Why I am very much successful, etc., etc. So all these things need to be understandable. That's why the new era, which actually people are started working in medical imaging, mostly on EAI point of view. XAI is basically gives you that overview that which particular feature is more actually impacting to the system for getting this accuracy. So that explainability needs to be there. So suppose this one, there is a, I mean, you can go through LIME also, which is called local interpretable, say, model agnostic, the explanations, where, see, suppose this is a Labrador. So this is a Labrador. This is given by a learning model. So any classifier will tell you, this is a Labrador. But why? Why it is a Labrador? Why should I trust you? So that's why we need to come up with a framework like explainable AI, like LIME, which is one kind of super pixel, which actually proves the stronger association. So if you go through this particular link, you will see the log codes are already available. So from there, this particular masking part is you will get. LIME will give you this masking part, and it will prove the stronger association with the prediction of Labrador. This explainable suggestion actually pre-trained in Session1. If you put it module, it gives you good prediction result. So that's why this LIME helps to increase the confidence in the machine learning model by understanding why it is returning certain prediction. So if you are getting the prediction result 0.9 or 9.5, why you are getting such kind of confidence? I mean, say confidence level. That should be interpretable by that framework, such as LIME, where we've established the strong association with the predicted result. That predicted result association is important so that we can think about it that, okay, this is basically the explainability of the model, why we are getting better results. So last one about the knowledge. The knowledge, if it is knowable and knowns, it's trainable. The knowledge which is knowable but unknowns, it's basically generalization, which we used to do. The knowledge which is unknown but knows certain class of system that deep learning can never learn, never be able to train that system. This is called unknown knowns. And the last category, which is unknownable unknowns, the class is totally ignorance. It's a metaphysical statement. Deep learning fails, which is called great firewall. So you have to rethink about the great firewall cases, the great firewall of knowledge, where all this knowledge-based system actually fails. So I try to give little bit of insight about what are the different areas which you can, what are the different challenges you can face in once you go for deep learning. I think from next session onwards, more deeper insight you will get from medical image processing point of view and how the deep learning different framework works, etc. In my later session also, I will try to cover this. But this was a very generic session, or what are the different challenges, or how can you cope up with those solutions. I tried to give a brief idea. But again, I'm very sorry for this today's session because my broadband was not working. So that's why I need to connect from mobile itself. So maybe there are lots of technical issues which you face today. Sorry for the inconvenience caused. Thank you very much. So if you have any question, please after stop sharing, you can feel free to ask. If I know, I will definitely answer. If I don't know, in my later class, I will try to answer or explain more. Thank you.
Thank you, sir. Any participants? Any participants would like to ask any question? Sir has completed the session, so I request participants if you have any question, you can raise your hand or you can write in chat box.
I am writing my mail ID also. So if anybody needs.
So I think no any other participants have raised their hand. Let me check. Okay. Thank you, sir. You started with machine learning application when you apply different machine learning application on data. So training data is very much important, sensitive. And you also explain about uh, overfitting problem, how we can reduce the overfitting problem reduction, how we can reduce, and you also explain about the classifier and machine learning for image classifier. So really, it was very interesting and it was informative session for all the participants who
Thank
are
you very
doing
much.
research in the field of medical image processing. So I think you have explained a lot of uh, like machine learning application, neural network, deep learning. So really, it was a wonderful session, sir. So
Thank you.
yes, sir. Now we can close the session, sir. So thank you, sir, for joining the session.
Okay. Thank you very much. Thank you all.
Thank
Good day all. Good day all, and happy Teachers Day again. Okay. Bye.
So participants, we have break for half an hour. So we have break for half an hour. So again, we'll meet at 12:40. So again, we have next technical session at 12:40. So we have half an hour break. Thank you all.